Okay, so here are some common discrete probability distribution. The first most common one, I guess maybe not common, but most of the easiest one to understand, and this is why we begin with this, is the uniform distribution. Okay? Now, visually, what you want to understand uniform distribution is just the distribution is, well, uniform. Right? So there, for every outcome, that is equally likely. Okay? So for example, I have a dice roll. Right? Dice roll has a uniform distribution. Okay, because I have outcomes 1, 2, 3, 4, 5, 6, and then the outcomes or each outcome has a probability of 1, 6, 1, 6, and so on, all the way through 1, 6, all the way through. Right? Coin flip has a uniform distribution, right? Because a coin flip, I have an outcome either, well, 0 or 1. If I let head equals 0 and tail equals 1, I have two outcomes, 0 and 1, and the probability, right, of each outcome is again 1/2 and 1/2. Okay. By the way, now we will start using this notation more and more. You've seen it already. F of x. Like this F stands for well, function, but this represents a probability density function. Okay, which will shorthand for PDF. Right? And this just means a function that gives the probability of the outcomes of each outcome of each x. Right? And here we have a uniform distribution, right? And here we, for example, for the dice roll, 1, 2, 3, 4, 5, and 6. We can divide this even to equal size. Right? The height of this rectangle is going to be 1, 6. Why 1, 6? Because the area underneath this whole thing must equal 1. Okay, that is true for all probability distributions. Okay. Now, so why do we need, or why are we interested in these probability distribution formulas? Well, if you look at, for example, let's take a look at the example above here. Here, this is a probability distribution. It is perfectly fine and adequate. However, if I wanted to calculate the expected value, or if I wanted to calculate the variance, there's no easy formula. I have to calculate it by the definition. I have to multiply each number by this probability and then add it up. Now, if I have multiple outcomes greater than 4 here, right, then you can imagine that could be very cumbersome. Now, what's convenient of learning a lot of these popular probability distribution is that we have a nice precise formulas or convenient formulas. Right? Now, so one of the things to understand here is knowing when are we able or are we allowed to use these formulas to model a particular experiment. Okay? So first, let's start with binomial probability distribution. Right? And this is, we can use this, right, whenever we have a binomial experiment. Okay, now what is a binomial experiment? Here are the criteria. First, an experiment consists of sequences of n identical trials. Okay, there are only two outcomes of each trial: success and failure. Okay, the probability of success, right, does not change from trial to trial. Okay, and the trials are independent. Okay. Now, what is independent? So we talked about this in chapter 4. Independent means if A and B, right, are independent, right, then that means probability of A given B equals probability of A. Right? It does not give any more information. Right? So the best example of, or the easiest example of binomial distribution is flipping a coin. Right? Suppose I flip a coin. All right. Suppose I flip a coin 10 times. Okay. So how many trials? N equals 10. I have 10 identical trials, right? Because every time I flip, it's the same coin. Okay. The probability of success. Suppose I'm looking for head. So then the head will equal success. And then so that in case tail will equal failure. And there's no other outcome possible. Okay? Now, the probability of success does not change from trial to trial. So every time I flip that coin, the probability of getting a head equals 1/2. Right? And that doesn't change. Right? That does not change no matter how many times I flip it. Right? And it does not change, right, depending on what I got last time. So if I get a head on the last flip, right? The chances of me getting a head on the next flip, it is still 1/2, right? They are independent of each other. Every flip is independent. Okay. If you have an experiment which satisfy these criteria, then you are allowed, or it is proper to use a binomial distribution to model it, right? And that will give a lot of that will give you a lot of advantages, right? Two. So for binomial distribution, there are two things you need first. One, number of trials, and two, the probability of success. Here is the binomial distribution formula, right, or the PDF. N and P are the parameters of the distribution, right? Right, and this is the formula here. So for example, right, for example, right, let's say that we have n equals 10, so 10 number of trials, and let's say probability of success is 0.7. So maybe this is a weighted, this is a lopsided coin. Right? So the question I might ask is, well, if I flip this, this coin 10 times, right, what is the probability that I will get, let's say, 4? 4 heads, right? Again, this is a lopsided coin, so the probability of getting a head equals 0.7. Now first, let me write the PDF. The PDF looks like this: f of x equals the probability of x equals this lowercase x here, and it is 10 to the x times 0.7 to the x times 0.3, 10 minus x. Okay, now I have my parameters plugged in, so now this is a proper function, and now I can use this to answer my question. So I want f at 4. Okay, here we go. So that's 10 choose 4. Okay, and then that is the 0.7 to the 4th, right, and times 0.3 to the 6th. Okay, so you can just go ahead and put that in your calculator, right, and then put the whole thing in your calculator, right? And if you get it right, then what you will get is 0.037. If you don't know how to use the calculator, or if you don't have a graphing calculator, there are numerous apps in the App Store that you can use. If you have any questions, please email me. Let me know. Okay, and then let's see here. So let's do one more. Suppose 4 out of 10 Americans are diabetic, and we randomly pick 10 people from the population and count the number of people who are diabetic. Okay, so the easiest way to understand this is to visualize yourself with a clipboard, and you're standing on the corner of the street asking people randomly, all right, are you diabetic? Right? And then what you put on the board is a yes or no. If the person you ask says yes, you check yes. The person says no, you check no. All right, so then you asking, right? So first you're asking 10 people, right? Okay, so what are the possible outcomes? It could be number of trials, so it's going to be 10. Okay, the probability of success, well, that's 4 out of 10. So my probability of success equals 4 divided by 10, which is 0.4. Okay, my f of x is going to look like this: 10 choose x, right, times 0.4 to the 10. To the x, right? Then 0.6 to the 10 minus x. Okay, all right. And then so since this is the probability of failure. What are the possible x values, or the values that the value that random variable x can take on? Well, if I'm asking 10 people, right, then my possible x value could be like this. All right, I can ask 10 people, and it could be that none of them, right, are diabetic. Very unlikely, but that is a possible outcome. Or it could be that only one of them are diabetic, right? Or 2 of them are diabetic, and so on. Okay, and I could get, right, again, unlikely, I could get also the case that where all 10 people that I asked are diabetic. Right? You can write it out like this. Right, we can write it in a table form: 1, 2, 3, all the way to, I got 0. I forgot a 0 here. 0, 1, 2, 3, all the way to 10, right? And then we can calculate the probability of each possible outcome. And that's what this is for. Like this probability, this PDF here is used for you to calculate the probability of each of these outcomes. What is the probability that I'll get 3? All right, I'll get 3 people who are diabetic. Right? What's the probability that I'll get 10 people who are diabetic? Okay, so let's give that a try. Okay. Again, I'm gonna copy down from the previous page. I'm gonna write down what the PDF is. So this 10 choose x, 0.4 to the x, and 0.6 to the 10 minus x. Okay, what's the probability of picking 6 people that are diabetic? Well, that's f at 6. Okay, f at 6. That's 10 choose 6, right, of 0.4 to the 6 and 0.6 to the 4, okay, which equals, you put that in the, again, send me a message if you don't know how to do this on your calculator, or you don't have a scientific or graphing calculator, okay, and this is going to be 0.111, okay, what's the probability of all 10? That's f at 10, okay, so that's 10 choose 10, right, and then 0.4 to the 10 and 0.6, right, to the 0, okay, equals, and if you put that in the calculator, by the way, right, what is 10 choose 10? Okay, so think about it. Before you put in the calculator, we can think about this one. This one's pretty easy. 10 choose 10, it means how many ways, right, if you ask 10 people, they're diabetic, how many ways can you get that all 10 people that says yes, right? And there really is only one way, right? Because if I look at 1, 2, 3, right, if I look at each person that I ask, right, as a kind of a slot here, right, and I ask 10 people, and they all say yes, 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 and all the way here to 10 yes. How many different ways can I arrange this 10 yes? Only one way. There has to be all yes. There's no room to arrange it any other way. So 10 choose 10 really is just 1. Right? 0.6 to the 0, well, that's just also 1, right? Anything to the 0 power is 1. So really, this just becomes 1 times 0.4 to the 10th times times 1, right? Which is just 0.4 to the 10th, which is 0.0003001. Okay, all right. And then what's the probability that no one's diabetic? F at 0. Okay, 10 choose 0. Same idea here. 0.4 to the 0 power, 0.6 to the 10th power. So again, 10 choose 0. If everybody says no, how many different ways to arrange that? There's going to be one way to arrange all that. 0.4 to the 0 power, that's also 1. Okay? Then now what we really have is just 0.6 to the 10th power, okay? Which is 0.00605. Okay? That's the probability there. All right. Let's try a second example. I have a college, 168 female, a total students, student population of 420. Okay? If I randomly pick 35 students, what's the probability that I'll get of the 35, I'll get 10 female students, okay? And go ahead and pause the video, give this a try, and then check your answer when you're ready. Okay, all right. So we can see here, my number of trials is 35, n equals 35. P, my probability of success, and in this case, I'm looking for female, so picking a female, it is considered a success, right? The probability of success is 0.4. These are the two parameters, right? So as a first step, you always get those two. Once you have those two parameters, then you plug it in your PDF, and then the rest is straightforward. I want to know what's the probability of getting 13 females, and there's my PDF setup. Put that in your calculator, and you get 0.13. Now, as mentioned before, one of the main advantage of using a well-defined formula or a function to model an experiment, right, is because it's very easy to calculate the expected value and the variance. Right? So here, right, if an experiment can be modeled using a binomial distribution, then we can go ahead and use it, and we can calculate the expected value and variance with these formulas. So let's calculate the expected value and variance for this experiment above. Okay? So the expected value of x, right? Remember, normally, right, if we just have the outcomes and the probability, we will have to sum it up. So it will be sum like this, right, and f of xi. Right? Now, if you wanted to, okay, you could, in theory, right, write out all the possible outcomes. So in this experiment, it would be 0, 1, 2, 3, all the way to 30, 34 and 35, okay, and so on here. And then you can use this PDF, right, to calculate. You can use the PDF to calculate, right, all these different numbers, right? For example, 13, we got 13 as 0.13, and you could use the PDF to calculate every one of them, and then after that you can multiply, right, and then add it all up. You will get the expected value, but as you see, that will take forever. So instead, right, our expected value of x, we can use this formula. It's just n times p. So just 35 times 0.4, okay, which then just equals 14, right? Much faster. Okay, what about variance? Well, that's sigma square. Sigma square equals the variance of x, right, which we would just use this formula. So 35 times 0.4 times 0.6, okay, that's going to give you 8.4, okay, very convenient. What if I want sigma? Well, that's just the square root of the variance of x, which is the square root of 8.4, which then just equals 2.898. All right, the next probability distribution that we're going to look at is the Poisson probability distribution. Okay? And just as the binomial, right? If you observe a random experiment that has the following criteria, then it is convenient to use this model to model that experiment. Okay? All right, now what is a Poisson distribution? So a Poisson random variable occurs when we are over a set interval of time or space. So a binomial distribution, like a coin flip, right? You flip a coin and you have a set number of times this experiment is defined. So if I'm going to flip the coin 10 times, then that is preset, that the experiment is set, right? Here, we're going to say the interval is set. So, so an example of a Poisson experiment, right, is, what if I flip the coin for an hour? Right? If I flip a coin for an hour, then how many heads would I see? Right? That would be a Poisson. That would be a Poisson distribution, right? Or if I drive a car for a mile, right? Or if I drive a car for 100 miles, right? How many potholes would I hit? Right? That would be a Poisson distribution. Right? All right, and so because what is set is the interval of time or space and not the trial itself, then the random variable, right, the x value, can take on an infinite number of values. So you could have, so in that interval, nothing could happen, or it could happen once, it could happen twice, and so on. Right? We're going to allow the number of trials to be infinite in this case, because it's not fixed. Now, the two main properties of a Poisson distribution, right, has to be followed. One, the probability of occurrence is the same for any two interval of equal length. So if I'm saying that, for example, if I drive for 100 miles, then on average, I will hit 20 potholes. Well, then if I drive for 50 miles, half that, then I should expect to see half that, so 25 potholes. Okay, so if I cut the intervals up, then the probability should scale accordingly. The number of occurrences are independent, and are independent of each other. So if I see a pothole, so if I hit a pothole in the first 20 miles, it should not affect the probability of me hitting another pothole on the next 20 miles. Okay? So they're independent. Every interval is independent of each other. All right. Now here is the PDF. Okay, there is only one parameter, that is mu. Mu is the average, and that is the only parameter that is in this PDF. Okay, and then and so once you have that, so for example, let's say that mu equals 5, right? Then my PDF will look like this: 5 to the x e to the negative 5 over x factorial. Okay? That gives me the probability of x, of observing x. Okay. Now, before I talk about side-by-side difference of binomial and Poisson, let's go to the next page, and I want to just give some example how to use a Poisson distribution. Okay. Suppose a bus that comes to a stop at a rate of 20 per hour and follows a Poisson pattern. Okay, so when you see that word, when a question says it follows a Poisson pattern, it just means that every interval is independent of each other. So we can say that every hour we're expecting 20, every 30 minutes we will expect 10. Every 30 minutes we can expect 10. So we can divide down the interval as such. Okay, write down the probability function. So here we go. All right, f of x. Now our mu, right? So our mu is going to be 20. Okay, so 20, right, raised to the x. Right, 20 raised to the x times e to the negative 20. Okay, over x factorial. Now here's the tricky part about the Poisson distribution is that the parameter has a time value to it. Okay, so in this case, right, 20, right, we have to be specific. We're saying that 20 is 20 per hour. Okay, and that will only work so. Okay, so that's the only way the Poisson will work is that you have to be specific about 20 per what is the interval you're talking about. So if mu is 20 per hour, then there is my probability function. Okay, what does x represent? Well, x represents the number of success, right, per interval. Sorry about that. Per interval. Okay, in this case is in an hour. Okay, and just again, always remind yourself what are the possible values that x can take on. It will be 0, 1, 2, all the way to infinity. Okay, all right. Now, what is the probability that no bus will arrive in a 15-minute interval? Okay, so now I need to change my mu, okay, because my interval has changed. This mu here used to be 20 per hour, so I need to change this. So I need to change this to how many buses do I expect per 15 minutes? Okay, so let's think about it, right? So it's a Poisson. We know that it's a Poisson pattern, so then it must be divisible evenly. The average number of buses, right, are distributed evenly across any fixed number of intervals. Okay, so one way you can think about this is, well, if 20 per hour, then how many 15 minutes are in an hour? Right? So an hour has 60 minutes, then they are a total of four 15 minutes intervals per hour. So I'm going to take 20 divided by 4, 20 per hour. So that will give me a total of 5 per 15 minutes. Okay, so I'm expecting 5 buses every 15 minutes. Okay, my PDF is going to look like this. Then be 5 to the x e to the negative 5 over x factorial. Okay, now I can answer the question. What is the probability that I will see 0 buses, right, over that 15-minute interval? Okay, so then just 5 to the 0, e to the negative 5 over 0 factorial. Okay, you can put that in the calculator, but let's think it through. Right, this is 5 to the 0, just 1. 0 factorial is also 1. Okay, right. So remember your factorials. There, let me just give a quick recap or a quick review here. Right, factorial, n factorial just equals n times n minus 1 times n minus 2 all the way down to 1, right? So for example, 5 factorial is 5 times 4 times 3 times 2 times 1, right? Then, so that means 1 factorial equals 1. Now, strangely, 0 factorial also equals 1, okay? Don't ask, it's just math, right? Just accept it, right? So then, if this is 1, right, and this is 1, then we really have just e to the negative 5 here, okay? Put that in your calculator, and then you should get 0.0067. All right. Try that. Let's now have the PDF. We can answer this very easily. What's the probability that 2 buses will arrive in 15 minutes? F of 2, okay? 5 to the 2, e to the negative 5, 2 factorial. Put all that in the calculator. We get 0.084. All right. Okay. Now, let's look at this question. What's the probability that 2 buses will arrive in a 20-minute interval? So now, careful, the interval has changed. We went from 15 minutes to 20 minutes. So then we need to adjust our mu, right, to 20 minutes. So if you adjust your mu, you ask yourself the question, how many 20 minutes intervals are in an hour? Okay, and that is 3. So then I need to divide the original 20 by 3. Okay, and then I will get 6 point, right, and then 66667. So let me just go round to 67. Here's the thing about Poisson distribution. mu does not need to be a whole number. You could put decimals or fractions, right, as mu. Now let me try this again. Probability, here, f at 2. Okay, now my mu is 6.67, so 6.67 squared, right, times e to the negative 6.67 over 2 factorial, okay? Put that on the calculator, you get 0.028. All right, now let's challenge our understanding of the Poisson distribution a little bit further. Here I have two Poisson distributions, both in the distribution is written out in table form and also graphically. Okay, so you can see here, right, the probability for this one, the probability that x equals 0 is 0.74, and here we see 0.74. Okay, and it trickles down like this. Here's a question for you, right? I have a mu1 here and a mu2. Okay, so these are two different mu's here. Which one is bigger, right? Mu1 versus mu2, right? 1 or 2, which one is larger? Okay, so pause the video, think about it, and start and restart when you think you have an answer. All right, so I hope you guess mu2 is bigger. Okay, mu2, which is the average occurrence over an interval, right? Mu2 is larger. Okay, so mu1 is less than mu2. Okay, now we don't have any, there are actual numbers, but let's forget about numbers. Let's see what characteristics can we see, how do we answer that question? Well, I think, there are a couple ways to do this, but I think the one dead giveaway is looking at the probability of 0 occurrences, right? If you look at a Poisson distribution, remember, the mu in a Poisson distribution represents the average rate of occurrence in that interval, right? If you have a high mu, right, meaning a high average occurrence, then what do you think that would do to the probability that you observe 0 occurrences in that interval? Then that should be pretty low, right? Like if you say, well, it is very, if the average is high, then you should not expect this, right? You should not be able to, over that interval, you should not be able to see no occurrences at all. So the fact that this one, right, the fact that mu1 gives you such a high probability of no occurrences, that should tell you that mu1 is very small, right? Whereas mu2 is going to be bigger. Okay, so whenever you look at the histogram, look at this, right, you want to think about this will help you kind of understand what does mu mean in a Poisson distribution. Okay, so flip it back over to the previous page, right? We can do a side-by-side comparison now, and I think this will really help you understand in what situation you can use a binomial to model your experiment or a Poisson to model your experiment. First of all, random variable x, right? In both cases, they represent the number of success. Right? How many time in this case, how many time in that n number of trials, right, is successful? How many time in that interval is do you observe the success? So the observation for binomial distribution is over n trials. Right? Think flipping number of coins or asking fixed number of people the survey question. Now for Poisson distribution, it's a fixed interval. Okay, so that's either time or distance, usually. Okay, now the number of trials for binomial distribution is fixed at n, right? Because I'm flipping the coin 10 times. So that's in those 10 trials, I'm going to observe how many times I get a head, right, or a tail, right? But for Poisson distribution, right, I don't have a set number of trials because I'm just sitting there over this period of time or going up with this distance, and so the number of trial is not fixed, right? All right, not fixed, and in fact it is infinity. Okay, parameters. So for a binomial distribution, my parameters are n and p. For Poisson distribution, my binomial is only mu. My PDF probability distribution function is n choose x, p to the x, 1 minus p to the n minus x. Right? For my Poisson distribution is mu to the x, e to the negative mu over x factorial. Expected value. All right, now this is why we like well-defined probability distributions, right? Because we can calculate these very quickly. So expected value is binomial distribution. Variance is n times p times 1 minus p. Okay. What about for Poisson? Well, expected value, you should be able to guess that because look, the parameter, right, is mu. Right? So the expected value is just mu. Right? Once you have mu, that's what you should expect. Now, what's really surprising and convenient is that sigma square for variance, right? This is also mu. Magic. Okay. All right. One last example on the last page here. So go ahead and read the problem, right, and see that this follows the Poisson distribution. How do we know? Because the problem says the passengers arrive randomly and independently. Okay. And it gives us the mean arrival time. So right away, we can write down the mu here for 10 for per minute. So mu equals 10 per minute. Okay. Again, every time we write down the mu, you need to specify what is the interval that we're talking about here. All right. Now go ahead and pause the video and try these questions out. Try these questions out for yourself. When you're done, go ahead and unpause and check to see if you're on the right track. Okay, let's continue. Okay, so first we can write down the PDF. So f of x is 10 to the x, e to the negative 10, and x factorial. Okay, now secondly, let's do part 8 first. So a, probability x equals 0, 1 minute period. So we already have the mu as per minute, so we no need to adjust for the mu here. So go ahead and plug that in, and we get this. So this means that what's the probability that in 1 minute there would be no arrivals, right? Okay, next. Now, what's the probability that 3 or fewer? Okay, so this is a little trickier because look, I need the probability of x is less than or equal to 3, so I need all these 3. So I need 1, 2, 3, 4. Okay, and these 4 will be 0.0103. Now, I will need to calculate. Also, I will need to calculate these independently, right? To get and each of these, right? To add up these to add up these numbers. Right? So let you try that on your own. Now, there's also a way to do it in the app here. Okay, so on this app, you can find it if you Google. If you look in the App Store, just look up probability distribution. Here's the developer that you want to look for. Oh, that will be this. So this is the app that we're looking at. Look up Poisson distribution. So it's going to be the last one here. Okay, there's only one parameter you need to put in. Now lambda means mu. Okay, so so in this case we'll put in 10, and the x value that we're looking for, right, is going to be, so for example, right, I want x equals 0, so you put in 0, and then voila, you get 0.0005. Okay, if I want 1, okay, then I'll get 0.00045. Okay, and then so on. I'll get, if I want 2, I'll put in 2 there, and then I'll get 0.00227. Now, what this app is very convenient is I can also look at less than or equal to. Okay, so here we go. Let's say I want 3. So I want less than or equal to, and that will give me all of the sum of all that. So you can use this app to look these up individually, or you can just use this to look it up all of it together. Okay. So let's continue. What's the probability that no arrival in a 15-second period? Well, first, right, we know that the time interval has changed, so we need to change our mu. So our mu, right? First, you need to take how many seconds are in a minute? 60 seconds. So divide that by 15. That'll give you the fraction there, and then divide 10 by that, which you would get 2.5. So that means on average, right, there is 2.5 arrivals in a 15-second period. Okay, plug that in. This is our PDF. Okay, and then we get that. Now, finally, the last part here. What is the probability that I'll get at least one arrival in a 15-second period? Now, visually, right, this is kind of what you want to visualize, right? I want probability of x is greater than or equal to 1. Okay, then. Right, you would need to, if you do this manually 1 by 1, you need to add up all the way from 1 to infinity. Clearly not possible. Okay, so we're gonna take the the complement, right? The probability of x greater than or equal to 1 is equivalent to 1 minus the probability of x less than 1. Okay? You can visualize it like this. If you write out all the possible x values here, right, then we know that is from 0 goes all the way to infinity, right? What we really want is this last portion here, okay? But however, right, that's too long to calculate, right? But we do know that everything must add up to 1. Okay, then if I take 1 minus the part that I don't want, which is the probability of x equals 0, then I'll have the rest of it. Okay, and that's exactly what I'm going to do. Yeah. So I'll take 1 minus probability x equals 0. I have that already. I calculated that earlier. And then now equals that my answer. Okay, so that is it for chapter 5.